Okay, hello everyone. Welcome to episode 38 of Warsaw Quantum Computing Group Meetup. Today, Oskar Słowik will give a talk, Transpilation of Quantum Circuits. So as usually, this meetup is recorded, so the video will be later available on our YouTube channel, hopefully. And if you have any questions during the meetup, please post your questions on our chat. And I will try to just read the questions later during the Q&A session at the end, or maybe during the lecture if there are some urgent or important questions. Oskar, would it be fine for you to just interrupt during the lecture if there are some important questions?
Sure, no problem.
Okay, so then it will be more interactive, maybe. Okay, and before we start, we would also like to thank our strategic partners, START and COVID, for supporting us, and thank our honorary partners, help us in advertising this event. And I think that I can stop sharing now. So Oskar, if you are ready, please just start sharing your slides, and the Zoom is yours.
Okay, so can you see my slide?
Yes, yes, I can. Yes. Mm-hmm.
Okay, and can you see my cursor?
I can see it.
Okay, great. Okay, thank you, Pavel. So, hello, my name is Oskar Słowik, and I'm a PhD student at the Center for Theoretical Physics, the Polish Academy of Sciences, and my PhD work is mainly mathematical physics related to quantum computing. And today's talk will be about the process of transpilation of quantum circuits. So first I will give some introduction where I will describe what is a transpilation and why it's important. And then I will move to Q-SCHI transpiler. So I will describe in more detail how this transpiler works, what are the options, and I will supplement this with some examples how it works. So how the transpilation process is going, and of course I will give some summary. So let me start with a description of the current situation in quantum computing. So we all know that current quantum hardware is very noisy, imperfect, and it doesn't contain a lot of qubits. So we call this noisy intermediate scale quantum computing. Actually, this figure is from 2018. So as I see, the prediction was that within 5 years, so in 2023, we will be in a somewhere around 1,000 qubits. I'm not sure if it's, well, I guess, I'm not sure if it's quite right, but I think we'll need to wait a little bit to see how the situation will develop and whether we will be able to go into this fault-tolerant region, hopefully. But today we are in this region, and we should focus on ways of extracting as much as possible from what we have. Now, I would like to mention the concept of quantum volume. So the quantum volume is, you can think of it as a kind of a benchmark for a quantum computer. So actually, this concept has evolved, and it has some much more precise meaning than it had a couple of years ago. So there is a specific benchmark based on random quantum circuits you can run on your quantum device, and you will obtain some score, which quantifies how useful your quantum computer is. So this score roughly depends on number of qubits. So the more qubits we have, the higher the score, and the error rates. So the lower the errors on in the quantum computer, the higher the score. So that was the idea, and it has evolved to, as I said, some precise procedure. So in fact, this quantum volume quantifies the largest square random circuit that the computer successfully implements. What successfully means here is, I know it's ambiguous, but it has some precise definition, but I won't mention it here. And maybe I will just say what the square here means. So the quantum circuit has a depth and it has width. And so width is basically just the number of qubits. So square random circuit is just a random circuit that has the same width as depth. And this quantum volume depends on many factors. Of course, it depends on a number of qubits, on the errors, on gate errors, on infidelity of the initialization, on some crosstalk, on the measurement errors, coherence problems. But it depends on also on the coupling map. So, okay, so it's a part of the device, but it depends also on the circuit optimization. So this is why I'm also one of the two reasons I'm mentioning quantum volume. So in fact, this transpilation or compilation can be used to improve quantum volume by using some techniques which were recently developed, but I won't mention them because they are a little bit more involving. So today I'm gonna discuss just let's say more easier passes of the transpiler, let's say. Okay, so moving on. Okay, so this is just to show, to visualize the progress in terms of quantum volume. So right now we have Montreal system available with quantum volume 128. So I guess this is the best quantum IBM's quantum computer in terms of quantum volume that's available online. Yeah, so now moving on, what does it mean? What does this part here about coupling map means? So in different implementations of, well, different implementations, physical realizations of quantum computers are linked with different constraints to the connectivity. So some have actually much better connectivity between qubits, some have worse. So in case of superconducting circuits, so IBM is using this kind of computers, we have some natural constraints on which qubit can be coupled to what qubit. And this is a visualization of this coupling map for, so here is a quantum chip below, above this diagram, and below there is a coupling map that corresponds to this, well, basically reflects the structure of this chip and what are the couplings implemented in this chip. So, and of course there are different topologies of these qubits, but there are also other differences. Those qubits, each quantum computer can have different sets of basis gates, but actually in case of IBM devices, this is always the same set as far as I know. I will mention it later. I'll discuss this basic this set later. Among other differences, there are of course differences in readout, errors in C0 errors, in single qubit operations, etc. So the qubits differ in quality, and this will be important later for the transpiler. So so this is actually IBM Washington. It has 127 qubits, and I placed it here because this is the highest number of qubits I found actually online. But it has quantum volume 64, whereas this Montreal, which is the best, has less qubits, but it has higher quantum volume. And for today, I will use IBM Q Santiago. So I ran some experiments and I will show you some results from the real hardware. And IBM Santiago I chose because it has particularly simple coupling map. So as you see, it's a chain. So 0 can only talk with 1, 1 with 2, 2 with 3, etc. But 0 cannot talk with 4, which will be important during the example part. So talk in a sense that I cannot implement 2-qubit gate between them. And in this case, this 2-qubit gate is control X because this is the only 2-qubit gate in the basis set. So let me define what is the transpilation. So here, by transpilation, I will mean the process of rewriting some abstract quantum circuit into an equivalent one that is compatible with a target quantum device. Compatible in a sense that is compatible with the constraints of this device in terms of connectivity, number of qubits, things like that. So it actually can be run on the device we have. And it has two key components. So the first component of the transpilation is ensuring compatibility. So to obtain equivalent quantum circuit that can be executed on specific quantum hardware. But there is also the second part, optimization. So we want to find an implementation that optimally utilizes available quantum resources we have in a given chip and minimizes the effects of failures and decoherence. Because as I showed you, qubits vary in quality. So it will be important which qubits, it's important which qubits we are using. And from this description, it is clear that transpilation is essential for the execution of quantum circuits, at least for non-trivial ones. And because we have the transpiler, quantum developers can restrict to thinking of abstract device agnostic quantum circuits. So they can forget about these constraints. They can just do, create nice quantum algorithms and do not think much about these constraints because the transpiler will do all the heavy lifting for them. So an abstract quantum circuit, by abstract quantum circuit, I mean what you are coding in QSKIP, right, before the transpilation. So your, let's say, your, well, it's usually humans think in some certain way, and it's easier to us to use some sets of gates, and then we can use these sets of gates or more qubits, and I mean maybe not more qubits, but do not care about this connectivity issue, and then the transpiler will enable the execution. And finally, this optimization is essential for maintaining high fidelity of quantum circuits. And this is particularly important for this noisy hardware we currently have, which does not have error correction and things like that. So you can do a very simple experiment to actually observe how this transpiler works in a very simple, on a very simple example. So we can start with a trivial circuit, and you can add Hadamard gates. But the point is that you should add pairs of Hadamard gates so that they, in theory, they will cancel out because they are their own inverses, right? So in theory, you are still implementing the identity gates everywhere. And you can increase this depth of this circuit and do the measurement. So when you will do the measurement, you will notice that the result does not depend on the circuit. It's the same for 1 million layers as for 0 layers. So this is because the transpiler noticed this cancellation, and in fact, what is really run on a device is just no Hadamards at all. So that's why the result is the same. But you can, for example, you can disable the transpiler, but if you don't want to do so, you can just add barriers, because barriers prohibit the cancellations or any operations between barriers that can modify the circuit. And then the transpiler is unable to cancel these Hadamards. And then you can increase this depth and do the experiment. So this is the result for depth 0 and for depth 10. So of course we are expecting the string of zeros, right? So now for 100 and for 1000. So as you see, for 1000, we have only 0.3, around 0.3 for getting the correct result, which is in contrast with the initial value of 0.95. So as you see from this trivial example, a compiler is actually something very important. Now, a little bit about the data structures which are used in this inner working of the transpiler. So the transpiler, as I will mention later, transpiler is based on some passes. So these are some operations, and these operations are in fact performed on a graphs. And these graphs, so for example, here I have a quantum circuit, and I can produce DAG from this circuit. So DAG stands for directed acyclic graph. So this is a graph whose edges are directed, and it does not contain any cycles. This is due to the, say, causality of this circuit, right? So this is the corresponding DAG. So it has, so green, let's say these green things are the entry points. So these are our classical and quantum registers. And we have some operations, gates or measurement, 1 to qubit. Arrow indicates that, let's say the flow, right? And finally, the red ones are the targets. So these are our qubits or classical registers. And as I said, the operations are performed on this DAG, in fact. So let's start with some simple operation. For example, apply operation back. So this will apply operation at the very back of this graph. So here I'm adding Hadamard gate on Q0. So now notice the change on Q0. We should look at this red Q0, and after the operation, you'll see that the Hadamard gate has been added. So this is called apply operation back. Of course, we can do apply operation front, and here I want to add control Toffoli gate, CCX gate on Q0, Q1, Q2. So you should look at green Q0 because somewhere will happen here. And yes, now you see, I will show it again. I'm adding this front using this operation front operation, Q0, Q1, Q2, and you can see that CCX is indeed the top of this DAG. And the last operation, let's say this kind of elementary operation of the DAG, is that I can substitute any node with some other DAG. So I'm constructing a mini DAG, which is a DAG circuit with 2 qubits, and it has control Hadamard operation on P1 and P0. So this P is just denotes the quantum register. And after that, I apply 1 qubit gate U2 on P1. So this is my mini circuit. I will inject, it will substitute the chosen target nodes, and my target node is CX gate. So after this operation, substitute node with DAG, I'm indeed having this CH with arrow Q1, U2 instead of CX. Okay, so this is just to, I won't focus on that later, but I just wanted to let you know what's going on inside the transpiler, what data structures are used. So, and finally, well, a very important step, I can transform this DAG after the substitutions back to a quantum circuit. So I'm using DAG to circuit. And this is the circuit before and after this DAG manipulations. And in fact, transpiler, all the passes of transpiler which are modifying DAG, because there are some which to just collect information, I'll mention it later, they are doing some operations on DAG. And that's it. And it's just conversion of, well, I'm simplifying a bit, but it's basically a conversion of circuit to DAG, some manipulation of DAG and going back. So as you see, this is my transformed circuit. So the pipeline for the transpiler, okay, so the transpiler works using a pipeline of operations. And in fact, these operations, well, these operations are called passes. So they are transpiler passes. And you can specify what kind of passes you want to use. So this is very flexible. Moreover, you can define your own passes. So if you have an idea how to modify DAG, you can write a transpiler pass, and you can just use it using a pass manager as any other pass. So there are some passes which are predefined given in QScript, and you can write your own passes. You specify the order of these passes, and you send it to the pass manager. So here's an example, some example how these passes might look like. So for example, we have on the left, we have our virtual circuit, our idea, what we want to have. So the first step might be virtual circuit optimization. Then we need to decompose all more than 2 qubit gates into 1 and 2 qubit gates. Then we do the placement of physical qubits, which is called a choice of layout. I will describe it in more detail in a second. Then we need to do this routing on restricted topology, because not well, given qubits usually cannot talk with all other qubits. I mean, yeah, this is just because we have some chip which is planar and things like that. Then we need to translate to the basis gates, and well, at some point we always need to do it, right? And we might have some physical circuit optimization. In fact, we might have passes which are done after the pulse scheduling. So, you know, in the end, we need to have some instructions for our hardware which in this case are some microwave pulses, controlling pulses. So pulse scheduling is like even a step after this. We have this circuit. We need to transform it into this sequence of microwave pulses. I mean, we are usually not doing it, but if we have access to so-called pulse level control, if we have access to the pulse level, then we can in fact do our own pulse scheduling. But anyway, some of the pulses can be also applied after the scheduling, which is in fact one of the ways to increase quantum volume by using some smart ways of improving this part. So pulse efficient things. Okay, but in general, the logic is, I mean, it might be kind of complicated. You might have various loops inside which are iterating until some, for example, depth is not increasing or things like that, etc. So okay, so here is like a list of all the passes that are currently available. Some of these passes are modifying the DAG, so they are insertion passes. They are in fact modifying the circuit, but some of them are just collecting some information about the circuit, for example, its depth or things like that, or more complex information, counting operations. I just place it here to show you that we have quite a lot of these passes, and some of them are applied after the pulse scheduling. Okay, so now I will describe some of these steps. So let's start with the layout. So as I mentioned, we need to map our virtual qubits to the physical qubits on a device. And usually we have, well, we always have many ways to do it. And we have also many layout passes in the transpiler that might have, well, they have different effects in general. So first, the most trivial thing is the trivial layout, which just goes 0 to 0, 1 to 1, just as they are numbered. There is a dense layout, which finds the most connected subset of qubits, and then, that's it. There are some more complicated approaches. Sabre layout, CSP layout, and VF2 layout, and these are they are based on some more complicated procedures. Like Sabre layout is based on iterative bidirectional routing problem. CSP layouts, the CSP stands for constraint satisfaction problem, because this is basically what we have here mathematically. The VF2 layout uses subgraph isomorphism problem, a way to solve the subgraph isomorphism problem. Because we have a coupling graph, we have our qubits, and this can be reduced to finding a subgraph in this coupling graph. There are some solvers. So, for example, this uses VF2++, which is an improved subgraph isomorphism algorithm. These are some, this is like a part of a research, kind of recent research. So interesting solutions. And last but not least, we have noise adaptive layout, which is based on some other paper, noise adaptive compiler mappings for noisy intermediate scale quantum computers, where we are trying to find a layout which is the best in terms of the taking into account the noise that is present on the device. So this is some heuristic. Now let's move to another problem which Transpiler needs to address, which is the routing. So as I mentioned, we have some restricted connectivity. And let's imagine we are using the Santiago chip, which has linear connections. So Q0 cannot talk to Q4. And let's say this is my virtual, this is my circuit I want to run. So obviously I cannot run it this way because I'm using CNOTs between Q0 and Q4. So let's assume this is like, I chose like a trivial layout. It's like this. This is like, and now I need to do routing. So there are various ways, but basically they are all based on inserting swaps. Okay, so here it's not Santiago, but it's like analog of Santiago. It has just, I mean, it doesn't matter. I can delete in this coupling map. I can delete this the highest numbers. So yeah, so basically that's Santiago. So let me show an example. So the basic swap is just, as you see, in order to implement this Q0, Q4 CNOT, I'm just swapping Q0 with Q1, Q1 with the Q2, and Q2 with Q3. So I have effectively qubit 0 at the place of qubit 3. Now I'm doing these two CNOTs. So I'm in fact doing Q0, Q4 CNOTs, these two which I want. Then I'm going back a bit with this swaps. So I'm unswapping kind of to move this Q0 to Q1. And the next gate, the third CNOT gate, is between Q0 and Q1. So that's fine. But it will be reversed because my Q1 is at the place of Q0 and Q0 is at the place of Q1. So that's correct. And then I will, if you just look at this a little bit, you will, you should see that this is doing exactly what we want. So this is one of the ways. There are another ways. I won't describe them. I just wanted to show you that there are many options here. So another way for solving the routing problem is a look-ahead swap and a stochastic swap. So maybe I should also mention that when choosing a layout, it may happen that we do not need any routing at all because it's called a perfect layout, I guess. So let's call it a perfect layout. So a perfect layout is a situation where I have such an assignment, such a choice of layout that I do not need to use this swapping at all. Yes. So yeah, I guess that's clear. So let me move now to the base gate set. So I just wanted here to briefly tell you that there are so this what are the most common set of base gates in IBM devices. So this is a control X, rotation about the z-axis, Sx, which is a square root of X, and X gate. But also during this transpilation, it is useful to use U1, U2, and U3 gates, which are just the compositions of rotations. Let's say as intermediate steps or something like that. This is, at least this is how I understand their usage. For example, yeah. So in fact, you may ask why I need U1 and U2 if I have U3. U3 is just an arbitrary unitary, right? So if I have U3, I have U2 and U1 because these are just special cases of U3. But I guess it's because U3 is much more noisy than U2 and U1 is the less noisy. So if we are able to use as much U1s as possible and U2s and not use U3s or use them just once at a time, then it's beneficial. So I guess this is why they are often used as these intermediate steps. Okay, so now I wanted to show you how the unrolling to 1 and 2 qubit gates looks like. So I created a random 3-qubit unitary, sampled from the uniform distribution with respect to the Hall measure on the unitary group. And I use the unrolling. So this is how it looks like. It's based on 2 passes, unitary synthesis and unroll. And I'm just plugging into the pass manager with parameters. I'm plugging my circuit. And this is what I get. So as you see, like a random 3-qubit gate can be kind of messy after unrolling to 1 and 2 qubit gates. And in fact, it's not even in the, it's not yet in the basis I want, but it can be, it's just an unrolling part. So I don't really care about the basis at the moment. Okay, and another thing is unrolling to base gate set. So here we have basically 3 methods. I won't describe them in detail, but I just mentioned in the brackets what is the flow of passes which are used in all these 3 methods. So, and I will show you how to use this translator to take our circuit we did by track manipulation, and I will unroll it to base gate set using translator. So it's this is the result. So as you see, I have only gates I wanted. So okay, so maybe I didn't mention, I'm using the basis, this typical gate set basis, right? So so this is the result. Now I wanted to mention some other optimization passes just to which are used in something I will define, which are predefined pass managers. So optimize 1 qubit gates decomposition is a very useful pass that basically is looking for a 1 qubit gates that are consecutive and trying to reduce the number of these gates. So it's rewriting them using trying to reduce the number of gates, right? The resulting gates can be different, but the point is that to use least amount of gates to substitute a string of 1 qubit gates by shorter string. Next thing is the commutative cancellation, which is basically trying to use the commutativity rules of gates to try to look if after the commuting some gates, they will cancel. I will show you an example and then it will be more clear. But now I'm just mentioning some of the other passes. Other thing is to remove resets in 0 state, so unnecessary resets. Optimizing swap before measure, and I'll also, it will be clear on an example. So it's like getting rid of swaps just before the measurement, because they can be basically substituted by exchanging classical bits. And the similar reason we have removed the diagonal gates before measure, because diagonal gate just before the measurement can be removed because it does not affect the amplitudes, and we only care about the measurement results. And I just wanted to mention another interesting pass, which is crosstalk adaptive scheduling. And in fact, this crosstalk adaptive scheduling is one of these passes that are used after the scheduling. And it's based on a paper, Crosstalk Mitigation through Adaptive Instruction Scheduling. Before I will go to these examples, I will describe what are the preset pass managers. So QScript is equipped with preset pass managers. So you don't need to, choose manually all these passes. And as you know, because you are, I guess you are usually not doing it. So you're usually using transpile, right? And that's it. So it uses a default preset pass manager, which has all of some chosen passes written in which are ordered in some fashion, and they are doing all the job. And the only thing you need to do is to provide one parameter, which is the optimization level, which is a number from 0 to 3. So you have 4 optimization levels. Well, that's not actually true, because you can also pass some other parameters. For example, you can choose some methods, methods for unrolling, methods for a layout. You can provide layout, or you can choose some other methods. There are some arguments in these preset pass managers, but if you don't want to do it, you can choose all the defaults and just choose one number between 0 and 3. And this is the optimization level. So let me describe what are the differences between these levels, and then we move to the examples. So for the level 0 pass manager, it basically means no, it's doing its job, but no optimization. That totally doesn't care about optimizing anything. So there is no explicit optimization other than mapping to backend. This pass manager, okay, so this is like from the documentation. So just let me read it. This pass manager applies the user-given initial layout. If none is given, a trivial layout consisting of mapping the I virtual qubit to the I physical qubit is used. Any unused physical qubit is allocated as ancilla space. Now, the pass manager then unrolls the circuit to the desired basis and transforms the circuit to match the coupling map. And that's it. So now let's move to optimization level 1. So it's like very light optimization. It's just simple adjacent gate collapsing. So this manager applies to the first part is very similar. It applies if I specify the layout, it applies this layout. If I do not specify it and a trivial layout makes a circuit fit to the coupling map, then it's used. Otherwise, circuit is mapped to the most densely connected coupling subgraph and swaps are inserted to map. And also unused qubits are allocated as ancilla. Of course, we need to unroll to the desired basis, transform the circuit to match the coupling map. There is some kind of optimization, which is just the collapse of adjacent gates. So in fact, if I were to run this example I show you with this Hadamard gates, then optimization level 0 would not detect it. This trivial example will, it won't collapse it to identity, but optimization level 1 should collapse it because it is capable of collapsing such simple adjacent gates. Adjacent gates. Now moving to optimization level 2, the first 3 points are the same, and the change is in the optimization where we are using this commutative gains cancellation and redundant reset removal. Possibly there is something else here, but this is like from documentation, so I won't argue with that, but I think it's not actually completely as it's written. I mean, it's not the full truth. Okay, now let's move to this level 3, which is the most heavy optimization. I mean, it's goes without saying that the higher the level, the more computationally costly is this whole procedure and lengthy. So here we have, we can have noise adaptive qubit mappings and gate collapsing using commutativity rules and also unitary synthesis. So in terms of the layout, the beginning is very simple. If there is no perfect layout, okay, so search for a perfect layout can be done, for example, using this VF2 thing. But if there will be no such perfect layout, it's not, maybe it might not exist, but it may also cannot be found in a like reasonable time, and then it will be terminated. This search will be terminated. So if no such layout is found and the device calibration information is available, then the circuit is mapped to the qubits with the best readouts and to CX gates with highest fidelity. This part is the same, but in the optimization we have some extra operations, so apart from commutative gate cancellation, we have full resynthesis of 2-qubit unitary blocks, redundant reset removal, and also this, it's not written here, but this redundant swap removal, and also diagonal gates removal, which are just before the removal of diagonal gate just before the measurement. So yeah, so now just if we look at the code, we have like more, this is what's written in the code in the comments for level 3. So this is a little bit more precise. So let me just go through this a little quick, and we'll move to the examples. So first we have the unrolling to 1 and 2 qubit gates, then layout on good qubit, the layout. If calibration is available, then we are using layout on good qubits, otherwise the dense links. So as I said, if layout method is not set, we first try VF2 layout. So this is a method we should try to look for this perfect layout. If it didn't converge, it uses dense method. Then we are extending dark layout with ancillars using the full coupling map. We are swapping to fit to the coupling map, unrolling to the basis, fixing potential misdirections in the control axis, and in the optimization, in fact, it's done in such a way that we are optimizing iteratively until no more change in depth. In fact, no more change in depth and in size. It has changed. I think they didn't change the documentation. As far as I mean, last time I checked for the source code, I think they changed it, and it's also it takes into account also the size. I think. Then we are removing useless gates after reset and before measure. So I already mentioned these operations, so I will show this on an example. And we are using commuting gates and optimizing contiguous blocks. So these are some kind of extra operations which are here. So let me move to this example. So I created this toy circuit, and it has some traps for the transpiler. So the first thing you can notice, oh, sorry. So this is a dark circuit, just to show how it looks like. So let's go back to this circuit. So the first easy task, it should be able to move these two axes, which are in the red box. The second thing is that if you look at this part, you can see that this also can be reduced to identity. And this is because of the commutation relations, because this X gate does commute with C naught. It's on the target part. So I can commute it with the C naught to the left. this X gate is sandwiched between C nodes. I can commute it with the C node to the left, and will cancel with this second X, and these two C nodes will also can be cancelled. So in fact, I can get rid of all of these guys in the red. Here you can see a swap, which is just before the measurement. So I can also get rid of this swap and just exchange the measurements, I mean the classical bits. And finally, from another simple trap is that I have S gate just before the measurement. S gate is obviously diagonal, so I can get rid of it. So let me show you how each optimization level handles this. So this is the output of the preset optimization level 0. So as you see, okay, so maybe I should also say that this unitary, this purple unitary is just some random 2 by 2, it's just some random 2-qubit unitary. Okay, no, so you see after level 0, this unitary is unrolled to the basis. We have these blocks. Nothing happened actually in terms of optimization. Actually, in this case, there is no need for routing, so this part is trivial here. So let's focus on optimization. As you see now, all of my little traps, they stayed here. We have still those two X's side by side. We have this X sandwiched by C node with other X. We have phase gate, etc. So let's move to optimization level 1. So at this level, as you see, those two X's on Q3 are gone, but my X sandwich with C nodes is still here. Also, swap is still here, but it's just unrolled to 3 C nodes. And my phase gate is still here. Now at the level 2, I need level 2 to get rid of these C nodes. So as you see before and after. So as you see, these 2 C nodes are gone and 2 X's, but we still have this these little traps, which are the swap and S gate. And at level 3, they are gone. So this is before and after. Yeah. But apart from that, nothing changed. So it's kind of a simple circuit. So here are some statistics I collected for you. So this is the optimization level. This is the depth and number of gates. So we have CX, SX, RZ, and X. So in fact, we are the most interested in the count of CXs because CXs are the most costly, the most noisy, etc. So as you see, we have 12, 12, 10, and 7. So optimization level 3 gives the best result. But in terms of depth, there is no change between level 2 and 3. It's still 23. Or maybe it's a mistake. Maybe even it's not 23. Is it 23? Okay. So maybe I remember, I guess maybe I did a typo, but I think this optimization level 2 had in fact smaller depth than level 3. And it doesn't really matter. Number of CXs is the most important here. It was not a huge difference in depth. And the second example is what if I take 3 independently selected unitaries, random unitaries. So here I will just show you the counts. So as you see, depth is without optimization is around more than 1,000, and we have 300 C nodes. Okay, so it was not a typo. It's this case which has smaller depth for optimization level 2. So as you see, depth goes down to 758 for level 2, and it goes a little bit up for level 3, but the CX count is almost, does not change between 0 and 2. It drops drastically by a third about between 2 and 3. So here the difference between, here the difference between this heavy optimization and no optimization is very, is apparent, right? Here it was, it's kind of, it was apparent, but it was not, well, it's still, well, okay, it's still a lot. But there were some cases where I was checking the statistics for some simple circuits, and it turned out that there is no difference between 2 and 3, or so so basically that's everything, and now I will just go to the summary. So to sum up, the transpilation is the process of rewriting an abstract quantum circuit into a functionally equivalent one that is compatible with a target quantum device. And its two components are ensuring compatibility and optimization. Transpilation is essential for the high fidelity execution of quantum circuits, especially for noisy intermediate scale quantum devices. Quantum QSKIT transpiler is highly customizable tool with various passes based on interesting heuristics. And it is equipped with 4 preset pass managers. Transpilation of quantum circuits is a challenging task, and it is an active area of research at the intersection of computer science, quantum physics, and mathematics. And that's it. Thank you very much.
Okay, thank you, Oskar. Do we have any questions to Oskar? I don't see questions on our chat now, but so let me maybe ask first questions. Okay, so I understand that this was basically about the transpilation process in case of QSKIT. Do you know if it's the same, or what are some other what are the differences in case of some other frameworks like PyQwheel from Rigetti, or for example, Penny from Xanadu? Are you aware of the work of?
I have no idea how Transpilation works there.
Okay, all right. So I believe that. So do you expect that there might be? So the way how the transpiler works may depend also on the hardware. So I mean the realization of a given quantum computer. I guess that it's also might be not very related to what you have been discussing here, but maybe you have some knowledge about it. I mean, for example, whether quantum computers built based on superconducting may require different transpilation processes than, let's say, quantum computers based on ion traps.
Well, I guess to some extent, yes, because as I said, in various architectures, there are kind of different problems with connectivity and things like that. But some problems will persist, I guess, right?
Okay.
So,
all right.
To some extent, yes, but I think not fundamentally.
Okay.
But that's my opinion. I don't know.
Okay. All right. And is there any mathematical formula to assess what's the time complexity of the transpilation process, and which factors have impact on the complexity?
Well, it depends on the implementation of the transpiler, because it's like a valid question. And for example, what parameters of quantum circuits affect, for example, runtime of some algorithms which are trying to find example, perfect layout or something, right?
Okay.
So I guess it's not clear. In fact, I'm currently working on some issue with QScript Transpiler, which is about VF2, and it's about trying to assess, because in VF2, there is some time for finding a solution, and if time passes by, then the search is terminated. Mm-hmm. But it does not really depend, it does not scale with this problem, yes? Okay. So the point is how to scale what is the reasonable time to for the search to run, how it depends on the circuit, how to assess it, how to assess the scale of the problem, how to calculate reasonable time. So it's unknown. Actually, I just started working on it. So
right.
I guess those sort of questions are not are very interesting and but are not easy.
Okay.
I mean, did I answer your question or?
More or less. So it's fair enough. So thanks. I can ask you later for details maybe or some references if necessary. All right. Do we have any more questions? Okay. I don't see more questions now. So I think we can finish the presentation part. So thank you, Oskar, very much. Let me maybe just share some final slides.
Thank you.
Okay. All right. Okay, let me just share once again. Okay, so we would like to thank once again our strategic partners, Norton and Kogi, for just supporting us, and our honorary partners for helping us in advertising this event. And we would like to invite you to attend our next event. It will be in 2 weeks from now, and Marcin Podzień will talk about reinforcement learning for quantum technologies. If you are interested in our events, let's stay in touch. Feel free to just follow our fan pages, channels, profiles, or join our groups, mailing lists. And I think that's all for today. So thank you very much. And now I will stop recording. Okay, so it looks at the recording